Hi everyone, so I thought today we could take a look at the review stations for Chapter 6. Chapter 6 Review Stations. Station 1. Station 1 says find the indefinite integral in each case. So we've got the integral of secant squared x dx, and we want to know what the antiderivative would be there. Well, that's going to be tangent x, and don't forget the plus c. Really, this is the time when you must remember your derivatives. All right, number 2, integral negative cotangent cosecant x dx. Whose derivative is this? No, this is cosecant's derivative. And don't forget the plus c. 3, pi plus x to the third dx. All right, so antiderivative of a constant is a constant times x, and the antiderivative of x to the third will be x to the fourth over 4. Okay. I think the next problem when I look at it with its radicals, I kind of want to get rid of those and turn those into rational exponents. So t times square root of t plus 1 over t square root of t dt. So when I think about this, that's t to the 1/2 times t to the 1. When we're multiplying and the bases are the same, we add the exponents. So this is going to be the integral of t to the 3/2 plus, hey, there's t times t to the 1/2 on the bottom. So that's going to be t to the minus 3/2. Now, what do we want to do? Well, remember, we want to add 1 there, and then we want to divide by that same number. So we're going to have t to the 5/2 over 2/5 plus, I'm adding 1 to this, t to the minus 1/2 over negative 1. Great. And if we tidy this up, 5/2 t to the 5/2 plus minus 2t to the minus 1/2. And just to confirm, I always think it's wise to sort of, okay, so I think this is my antiderivative, don't forget the c. Actually try and take the derivative of it. So I'm going to bring this down, and I'm going to get 25 over 4. And I don't see a 25 over 4 there. See? That little check for quality control, terribly, terribly important. If I now bring down the 5/2, that'll cancel with a 2/5. Yeah, and I subtract 1, I'm going to have 3/2, and that's exactly what I've got. And over here, if I bring down that negative 1/2, the 2's cancel, and minus times minus is plus, and I subtract 1, and I get the negative 3/2. So, yeah, I like that quality control check. Make sure you keep that as part of your process. Okay, and then the last one here, number 5, is the integral of 1 over e to the x plus x minus x squared dx. So, that to me is much easier than thinking about, should I use quotient rule here? Plus x minus x squared dx. So the antiderivative of e to the x is e to the negative, the antiderivative of e to the negative x is e to the negative x, but don't forget that minus, because you've got to undo that derivative of the inside function. If I take the derivative of this, it's going to be e to the negative x times the derivative of the inside function, negative 1. I don't see a negative 1 there. So there must be something present on the original function, so that when I take the derivative and have that negative 1 show up, negative times negative turns into that positive. I can't tell you how many students over the years, when they get to this problem, they do the antiderivative correctly here, and then they take the derivative of these. I don't know why. I really don't know why. Something about this problem, though. So don't take the derivative. Do the antiderivative. There. And, of course, the plus c. Fabulous, fabulous. Let's move on to station 2 now. Station 2 says a scared mouse's velocity in meters per second is given by v of t equals t squared plus 3 meters per second. T seconds. Use this to estimate how far the mouse ran in the first 4 seconds using 8 subintervals with both MRAM and trapezoid rules. Oh my God, Kukla, really? Okay, so if I'm graphing this function, I'm looking at something like this, and we're stopping at first 4 seconds. Okay, so that's going to be 16 plus 3. I've got an ordered pair here of 19. Now, if I'm looking for an approximation of how much distance the mouse ran during those first 4 seconds, I'm going to need some information, especially with 8 subintervals. Oh my goodness. So what's my t-chart going to look like? Well, if I do 4 minus 0 over 8, I see that the subinterval width needs to be 1/2. So 0, 1/2, 1, 3/2, 2, 5/2, 3, 7/2, and 4. Ugh. But wait, there's more, because while it's true that's the subinterval from 0 to 1/2, we actually need to know the height. We need to know, I guess it's the velocity, at the point halfway in between. So we need 1/4, we need 3/4, we need 5/4, we need 7/4, we need 9/4, we need 11/4, and we need 13/4. These are the values that I have to plug into here in order to get the velocity so I can do MRAM. Okay, clearly, if this is a calculator active problem, oh my goodness, I am so using the table feature of my calculator. But I don't know if the expectation is that or not. And based on what I seem to have written when I wrote the back of this station, yeah, I'm supposed to do this by hand. So t squared, that's going to be 1/16 plus 3, or 3 and 1/16, which I guess is 49 over 16. And then next I'm using 3/4, and I square that, and I get 9 over 16 plus 3. 9/16, 48, 57/16. And then I plug in 5/4, and that's going to be 25 over 16. And I guess I could just say that 3 is 48. So 48 over 16 plus 25 over 16 is going to be 73 over 16. And I plug in a 7/4, and that's going to be 48 plus 49, 97 16ths, 9/4, and the 81 plus 48 is 129 16ths. I'm going to put in 11/4. 121 plus 48 is 169 16ths. And finally, when we plug in that 13 over 4 and square, we're going to get 169 plus 48 is 217 16ths. So if I'm looking to do MRAM, my subinterval width is always the same, 1/2, and I'm just going to add up these values. So that's 49 16ths plus 57 16ths plus 73 16ths plus 97 16ths plus 129 16ths plus 169 16ths plus 217 16ths. Yeah, ideally, you're checking this over to make sure you haven't made any mistakes. And on free response, you can certainly stop here. Stop here. And that might be, in fact, a really smart thing to do instead of adding it all up. believe I added all of mine. Oh, let's trapezoid sum. What is that, man? I got 33 and 1/4 when I added all this up and multiplied by half. Okay. So there's our MRAM. That was very painful. But we're also asked here to do this as a trapezoid sum. Okay, so if I do this as a trapezoid sum, I do need the boundary. 3 halves 2, 5 halves 3, 7 halves 4. And we're still plugging values into velocity. So if we plug in a 1/2, if we plug in a 0, we get 3. If we plug in that 1/2 and square it, that's going to be 1/4. 3 and 1/4 is going to be 13/4. Nice. This will be 4. If I plug in 3 halves, I get 21/4. If I plug in a 2, I get 7. If I plug in a 5 halves, I'm getting 37/4. If I plug in a 3, it's going to be 12. If I plug in a 7 halves, 61/4. And finally, if I plug in 4, I get 19. So if I'm using my trapezoids here, because my subinterval width is the same everywhere, I can use that short form. 1/2 the subinterval width times 1 of the first height plus 2 of all these heights and 1 of the last height. So 2 times 13/4 plus 2 times 4 plus 2 times 21/4 plus 2 times 7 plus 2 times 37/4 plus 2 times 12 plus 2 times 61/4 plus only one of those 19s. And so that should be our trapezoid sum. And I end up with trapezoid sum getting 33 and 1/2. Again, this would be fine for free response, but if it's multiple choice that I'm answering, it's probably going to be this number. Okay, so let's take a look at this last question. This last question says, oh, and I guess that we're supposed to be calling these meters, because when we integrate meters per second times a number of seconds, we end up with, this is the number of meters the poor mouse traveled. Question 2 here says, evaluate this integral, t squared plus 3 dt. Okay, so that's going to be t to the third over 3 plus 3t. And since we're doing a definite integral from 0 to 4, I don't need to worry about the plus c, because those plus c's with this and this will cancel each other out. So I'm going to have 4 to the third over 3 plus 3 times 4 minus, and yes, please stay in the habit of plugging in the 0, because what I notice happens is students who just say, oh, that's going to be 0 whenever I plug in a 0, yeah, then finally they get to that place where it's cosine of 0, and they say, oh, I'm not plugging in a 0 because it's going to be 0, but this time cosine of 0 is 1, and you get the wrong answer, and we're both sad because you got lazy and always didn't plug in the 0. I'm plugging in the 0. So what do I have here? I have 64 over 3 plus 36 over 3, or 100 over 3, which is 33 and 1/3. 99 and 3/3. Yeah, that's it. And again, this would be meters. And so, well, what did we notice about the other ones? Well, our MRAM was 33 1/4. And our trapezoid sum was 33 1/2. And the actual value is in between, not halfway in between, but in between those two. So excellent. All right, there's station 2. I don't think I did anything as mean as 8 subintervals, but I would say, yeah, it's actually fair game on the AP exam. Okay, find the total area bounded by the curve and the x-axis given this interval. So station 3 is total area. And remember, when we talk about total area, we really want to remember that area always has to be positive. And I can almost guarantee 100% of the time that when you see the phrase total area, part of your curve is going to go below the x-axis. In our case, we have x to the third minus 4x plus 3. And that does factor. And oh look, my graph has intercepts at 1 and 3. And we're integrating from 0 to 5. We want the total area from 0 to 5. Well, there's my parabola. That's 0, 3. And I want to find not the integral, but the total area from 0 to 5. And so I'm going to break this up into some separate integrals. I'm going to say the integral from 0 to 1 of f of x, that's going to be this piece, minus the integral from 1 to 3 of f of x dx. Why the minus? Well, if I integrate from 1 to 3, I'm going to get a negative number as my answer. But total area is always positive. So if I subtract that negative number, I'll get a positive there. And finally, the integral from 3 to 5 of f of x dx. Okay? Now, as far as finding that integral goes, that should be pretty straightforward for us. We know that the antiderivative of this is going to be x to the third over 3 minus 2x squared plus 3x. And again, since I'm only going to be doing definite integrals here, I can just start evaluating. So this integral from 0 to 1, I'm going to plug in a 1. I have 1/3 minus 2 plus 3. And yes, if I plug in a 0, I get 0, 0, 0. At the very least, please make sure you check to make sure when evaluating at 0, you in fact get 0. So this is 1 plus 1/3, which is 4/3. Now what about the integral from 1 to 3? Okay, so we plugged in a 1 already here, and we know we got 4/3. But what about plugging in the 3? So 3 to the third is 27. 27 divided by 3 is 9. 3 squared is 9 times 2 is 18. Plus 3 times 3 is 9. Oh, well, isn't that interesting? 9 plus 9 is 18, minus 18 is 0, and so I just have negative 4/3. So minus a negative 4/3. Plus, what about integrating from 3 to 5? Well, isn't it interesting? When we plugged the 3 in, we got 0. That's plugging the 3 in there. Right, so that's 27 over 3. 3 squared is 9 times 2 is 18, and 3 times 3 is 9. So we know when we evaluate this third integral, that plugging in a 3 is going to yield us a 0. And so all I'm now concerned about is plugging in that 5. 5 to the third is 125 over 3. 25 times 2 is 50. And 3 times 5 is 15. Okay, and rather than try and turn this into a mixed number, I'm just going to make everything here with a common denominator. So this is going to be 150 over 3, and this is going to be 45 over 3. So we've got 170 minus 150 is 20 over 3. So minus and minus is plus. It's going to be 8/3 plus 20, or 28/3. There's our total area. This is not the integral from 0 to 5. If we wanted the integral from 0 to 5, we could do that. Or we could just integrate from 0 to 5. That's a very different thing because this negative stuff here, I'm reluctant to call it area, this negative stuff will nibble away at this positive stuff. In fact, this area turns out to be the same size, right? We have 4/3 and then another 4/3 over here. And so because we've got the 4/3 and the 4/3, then yeah, that's same. They're going to cancel each other out if this is an integral. And so the value of the integral is just this piece over here, or the 20/3. But we were looking for total area, not the value of the integral. All right, I think there's a second problem here. Yes, we now want f is x to the third minus 2x squared minus 5x plus 6 on -3 to 3. All right, and so here I feel a little challenged because this doesn't factor by grouping. And so I'm not necessarily sure how I'm supposed to break this up. Well, in a problem like this, since I can't factor by grouping, I'm probably going to use the calculator. I mean, what is it that we said last year? We said, hey, look, we live in this century. And so in this century, let's graph this thing and find one of the x-intercepts by reading it off the graph, and then we can use synthetic division to find the others. There was a method, and it's becoming less fashionable now, where I do the factors of this number over the factors of this number and create a list of possible rational roots, and I do a lot of synthetic division, and eventually I find something. Okay, so I did a quick graph on this on my calculator, and it looked like x equals 1 was one of the intercepts. Let's see if we can confirm that. Well, yes, we can, because we get a remainder of 0. We know from the factor theorem last year that when the remainder is 0, we found a root, and therefore we can turn that into a factor. This is certainly factorable as x minus 3, x plus 2, and forget the original x minus 1, right? Minus 1 because when I set that factor equal to 0, x equals positive 1. All right, so these are my x-intercepts. And I've got -2, positive 1, positive 3, third-degree polynomial with a positive leading coefficient. And my graph is going to look like this. And I'm looking for the total area from -3 to positive 3. And again, because I'm looking for total area, these negative bits here, I'm gonna have to flip the sign on those. So I would be thinking about this as the integral from 0 to 2, minus, because that integral is going to be negative, minus a minus is plus. Okay, dx, and then we want this one. That was -2, sorry. And that was -3. -3 to -2, plus the integral from -2 to positive 1, plus the integral from 1 to 3, except, see, I caught it the third time. See how this is below the axis? Well, that means that that integral will be a negative number, but since I'm looking for total area, I'm going to have that minus there. Okay, and so, and yeah, x to the 4th over 4 minus 2x to the 3rd over 3 minus 5x squared over 2 plus 6x. And again, we want to evaluate this antiderivative in all three of those situations. Alexa off. I'm going to let you do that, and I'm going to say that I got 31 2/4 as my answer when I did that. Okay? All right. Station 4. Station 4 says, given big f of x, find big F prime by taking the derivative of f of x. Okay, so we're given big f of x. And here we're told that big f of x in station 4 is integral from 1 over x to tangent inverse of t dt. Okay, and we want to know what big F prime is. Well, in order to find big F prime, I need to take the derivative of both sides. And so what I'm thinking about here is taking the derivative of an integral. This is FTC1 that we're talking about. FTC1 is what we're looking at here. So when I take the derivative of this integral, I'm going to have tangent inverse of 1 over x, right? Because derivative undoes integral, this goes in here, but don't forget the derivative of that inside function, negative 1 over x squared. This is not inside the inverse tangent. So negative tangent inverse 1 over x, and some squared x on the bottom. There's my derivative. Okay. So we're thinking all about FTC1. Okay, problem number 2. We're given f of x this time equals the integral from 1 to cosine x of t plus sine t dt. And when we take the derivative of both sides, we're going to get cosine x plus sine of cosine x times the derivative of the inside function, negative sine x. Okay? Hope that's okay. If it's not okay, talk to me. Let me know. But that's what I would expect. Derivative undoes integral. This goes into each of those places. Don't forget to take the derivative of that boundary. What about this? Well, think about it. What's the derivative of that constant? It's going to be 0. So, yeah, you could subtract plugging in the derivative of 0, the derivative of 1 into each of those places. It's just not going to get you anywhere. So I'm not going to. Okay, what do we have left here? We're looking for big F prime again. This time we have x to the third to 4 of 3t plus 2 dt. Well, remember our FTC1 only works if the constant is on the bottom. So big F has to be 4 x to the third, but I can't just randomly flip these boundaries unless I also put that negative in front. 3t plus 2 dt. So when I take the derivative here, derivative undoes integral. I have a minus out in front. And I'm going to plug this in for that t. 3 x to the third plus 2 is my answer. That goes there. Oh, times the derivative of the inside function. There you go. Where's that function? Okay. And this is the derivative of that. Yep, I feel good about that. And that was number 3 on station 4. Looks like my answer. Good. Okay, Even's got the negative, yes. And then the last problem here. Problem number 4 says big F this time is the integral from 4x to x squared of cosine t dt. Well, remember, we need a constant there. So we're going to use our log property to go from 0 to x squared of cosine t dt. And we're going to add to that 4x to 0. So think of this as here's 4x, here's 0, and here's x squared. And so we're doing this one from 4x to 0 plus this one from 0 to x squared. But wait a second, because we know that the constant has to be down here. So I want to flip these bounds, which means I need to pull out a negative. 0 and 4x. So when I come and take the derivative of this piece, I'm going to have cosine of x squared, don't forget the derivative of the inside, minus, and here, derivative undoes integral, this comes in here. Cosine 4x. Don't forget the derivative of the inside function. Okay, don't try and simplify that. Really, all you can factor out is a 2, because these are different. So stop, go away. Station 5. Let's take a look at Station 5. Station 5 says find the shaded area. And we're given a sine graph. And we're looking at here. This is y equals 1. And this is 3 pi over 2 negative 1. This is pi over 2, 1. This is 0, 2 pi. And we're looking for all this area. And there are a number of different ways we can, actually, we're given this point of intersection here at 5 pi over 2, 1. So that's the area that we're looking for. And again, you can do this problem lots of different ways. Some people say that this area and this open space are the same, so they could put that in there. And so what they think about is doing this big rectangles area and then taking away this piece, which is the integral of sine x from 2 pi to 5 pi over 2. Yes, of course you can do that. Yes, there are many ways to get this to work. But I think the one that most consistently and universally works is to think about, I'd like to add up the lengths of this infinite number of heights. And how do I find that length? Well, I'm going to take this number and subtract that number. I'm going to take this number and subtract that number to get that length. And so this length depends on wherever I am as far as x goes. And the way I've been talking to you about understanding this is to think about it as top minus bottom. When I do top minus bottom, I will get that length, whether the top function is above the x-axis and the bottom function is, or whether the top function is above and the bottom is below. Or even if they were both below, I'll always end up with this positive number when I do top minus bottom. Our top function is simply y equals 1. Our bottom function is this sine graph. And we want to integrate this situation for 0 to 5 pi over 2. I believe yes. 5 pi over 2. Okay, now let's think about this for a second. If I integrate here, I'm going to have x plus cosine x, and I want to evaluate from 0 to 5 pi over 2. Well, if I plug a 5 pi over 2 in here, I'm going to get 5 pi over 2. And cosine of 5 pi over 2? Well, cosine of 5 pi over 2 is going to be 0. Plus 0. Don't forget we need to subtract what happens when we plug a 0 in. If I plug a 0 in here, I get 0. There it is. Cosine of 0 is, in fact, 1. So my answer then, my total area, is 5 pi over 2 minus 1. And, curiously, this rectangle approach I was talking about, where this fills in that, and you've got to take a little away. Well, look, this rectangle has a length of 5 pi over 2 and a height of 1. There's 1 times 5 pi over 2. That's the area of the big rectangle. And where does this come from? Well, it turns out that 1/4 of a sine or a cosine graph has an integral value of 1. And so that's what we've got here. Okay? All right, so top minus bottom, always going to win the day. This is my answer. I feel pretty good about that. Yes, that's what I had before. And feel free to put units squared if you like. We weren't given any units, so I don't really feel compelled to worry about that here. Our next graph looks like this. It looks like a cosine graph. Looks like a cosine graph. We're stopping here at pi. There's pi over 2, and there's 0, 1. And we're looking for this area. And so here's the thing. There are a bunch of students who do, oh, this is the integral of cosine from 0 to pi over 2. And, well, yeah, that would be this, not the whole thing. And so you would still need to add the area of this rectangle. And that's going to be the distance of pi over 2 times and a height of 1. And most people don't see to do that. So really, I don't want to go any further down that road. I really don't want to go down the road of breaking this into 3 integrals and maybe having to do something here like the area of this rectangle minus the area of the integral. Oh, there's so many hard ways to think about this. Instead, what I want to do is just top minus bottom. Really, just top minus bottom. Because look, instead of having 3 or 4 integrals, I'm going to have from 0 to pi top function, cosine x, minus what's our bottom function, y equals 1. And that's it. That's all I need to do. Top minus bottom. The antiderivative of cosine is sine. The antiderivative of 1 is x. And I want to evaluate from 0 to pi. Okay, sine of pi is 0 minus pi. And I'm putting in the 0. Sine of 0 is 0. Oops. Nice. And I'm plugging in a 0 here. Okay, but clearly there's something wrong because this is turning out to be negative pi. And I know my area needs to be a positive number. So let's take a look again. Here's cosine. Yes. There's negative 1. Top minus bottom. The bottom is 1. Bottom is negative 1. So minus a minus is plus, and that should be plus. Okay, let's go back to evaluating and see what happens. If we plug in a pi here, the sine of pi is still 0, and here we get positive pi. And when I plug in a 0, I get 0 and 0 still. And so my total area is pi. All right, so area is pi. And you know, one way to think about this area as pi is this way. If I take this piece here, it fits perfectly in here. And so then I just have this solid rectangle whose length is pi and whose height is negative 1 on the graph. But because we're doing area, positive 1. So pi times 1 is pi. And so there's our total area there. I really, 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 really want to encourage you to think about using top minus bottom instead of splitting this up into 3 or 4 integrals. Almost always the people who do 3 or 4 integrals get the problem wrong, and I don't want that to be you. Okay. All right, let's take a look now at station 6, and we're supposed to evaluate the integral from 0 to 6, absolute x minus 4. And you know, a lot of students will get to this point in calculus and say, Mr. Cooper, I don't know how to integrate absolute value. To which I respond, yeah, me neither. Which is why I want you to appeal to the geometry of the situation, right? We know how to graph this. This is absolute value of x shifted right 4. And we're going from 0 to 6. So we're talking about this area. And so this is a situation from last December when we say, oh, look, I'm going to appeal to the geometry of the situation. 1/2, a base of 4, a height. If I plug a 0 in here, I get the absolute value of negative 4, which is 4. So this is 4. Now, this is the area of this first triangle. And we want to add to that the area of the second triangle. Well, I can see that 6 minus 4 is 2, but what about the height? I plug a 6 in here, 6 minus 4 is 2, absolute value of 2 is 2. And so there's the value of the integral. Again, if this is free response, you can stop here. This is 16, this is 4, that's going to be 20, half of 20, or 10. Now there is an alternative to appealing to the geometry of the situation, which I don't recommend using, but you could, is to rewrite this absolute value as a piecewise function, where you say, okay, this. So I've got negative x plus 4, and that's good for x values between 4 and 0. And then we've got this, which is x minus 4 from 4 on. Oh, I guess it's 4 to 6. And then I could integrate each of these pieces. But really? Oh my god, that's so much time. If I do that, just appeal to the geometry of the situation. So let's take a look at number 2. Number 2 says 0 to 4 of square root of 16 minus x squared dx. Now, you can't actually integrate this yet, because I haven't taught it to you. In fact, I'm not sure I'm going to be teaching that to you. Instead, what I'm going to say is, oh my goodness, this is the equation for a semicircle from negative 4 to 4 because of that. This is the square root of 16, negative square root of 16, and 0 to 4. But we're only looking from 0 to 4. That's not even half a circle. That's a quarter of a circle. So 1/4 pi r squared. What's our radius? Our radius is 4. 1/4 pi 4 squared gives me 4 pi as an answer. It's very easy to apply my geometry to this situation. It is going to be a big, I think impossible, challenge for you to do this integral by finding the antiderivative. So please appeal to the geometry of the situation. One might hazard a guess that Mr. Cooper made this station all about appealing to the geometry of the situation instead of finding the antiderivative. Now, I can understand here, I would rather do the integral and plug in 6 and 3/2, but let's take a look. So we have this line, and we're going from 3/2. Well, if I plug a 3/2 in here, 3/2 times 2, the 2's cancel, 3 minus 3 is 0. So I'm going from here to 6. And what shape is that? That's right, it's just a big triangle. We don't need this part over here, so all we need is 1/2 base. Well, the base is this length. It's not 6. It's from here to here. So if I take 6 or 12/2 and subtract 3/2, that's going to be 9/2. This length here is 9/2. Now, what about this height? I need that height to find that area of the triangle. So if I plug a 6 into this function, 2 times 6 is 12, minus 3 is 9. And so I end up with 81/4 is the area of that rectangle. I think if we went with the antiderivative approach, x squared minus 3x and evaluate it at 3/2 and 6, it's going to be 36 minus 18 minus 3/2 squared, and then minus a minus or plus 3 times 3/2. So what are we getting here? We're going to get 18 minus 9/4 plus 9/2. Like to make a common denominator everywhere, so 72 minus 9 plus 18/4. That's going to be 90 minus 9 is 81/4. And we've seen that answer before. So appeal to the geometry of the situation. And then our last one, problem number 4 here in station 6, from negative 2 to 4 of negative 1/2 x plus 3 dx. So we know what that graph looks like. There, we're starting at -2. We're going until we get to 4. Where is this intercept? Well, if I set this equal to 0, I end up with 1/2 x equals 3, or x equals 6. Yeah. Wait a minute. 6 is on the other side of 4. So I think what we can say is my graph should look more like that. And we're stopping here at 4. And this is where 6 would be. Okay, so we're looking for this area. That's just a big trapezoid. 1/2 height 4 minus a minus 2 times base 1 plus base 2. So if I plug a -2 into this function, -2 times -1/2 is +1 plus 3 is 4. And what about my height here at 4? Okay, 4 times -1/2 is -2 plus 3 is 1. And so I end up with 3 times 5, or 15. Yeah, I think that's pretty easy. I kind of think that's easier than doing -1/2 x to the second over 2 plus 3x, and now I've got to plug in a -2 and a 4. Yeah, I really don't want to do that, so I'm not going to. I'm going to move on to station 7. Let's go to station 7. Find the average value for each function on the given interval. Okay, so station 7, number 1, f of x equals x squared on -1 to 1. Okay, and we're looking for the average value. Let's think about what that means. We have an infinite number of heights, an infinite number of heights. We know if we plug a 1 or -1 in, this height will be 1 as a maximum on both sides. But we'd like to know the average of this infinity of heights. And we're going to do that by doing 1 over b minus a times the integral from a to b of f(x). Okay, this is not an area question. This is not a top minus bottom question. This is just find the average value. So I'm using my average value formula. Okay, that's going to be 1/2 over there. Antiderivative of x squared is x to the third over 3. And we're evaluating from -1 to 1. So if I plug in a -1, -1 to the third is still -1. I've got -1 over 6. But remember, I'm subtracting that amount from plugging in a 1. If I plug in a positive 1, I get 1/6 again. And so my answer is going to be 2/6 or 1/3. So that's not the area. That's the average value. Average of all these heights. This height is 1. This height is 0. The average of all those heights is a height of 1/3. So I think the way we understand that is, if I draw that line, y equals 1/3, then this area fits there, and this area fits there. Okay, average value. There are some more here. Number 2, average value cosine x on 0 to pi over 2. Okay, so if I think about cosine starts high, comes down, here to pi over 2. And again, I see an awful lot of heights between a height of 1 and a height of 0. And I want to find the average of all those heights. So I'm going to use my average value formula, 1 over b minus a, times the integral from a to b of f of x dx. So that's going to be 1 over pi over 2, or 2 over pi. And here, when we do the antiderivative, we're going to be looking at cosine x. We're going to be looking at sine x. from 0 to pi over 2. Okay, if I plug a pi over 2 in there, I get 1. If I plug a 0 in there, I get 0. And don't forget to multiply by this constant. And so our average value is 2 over pi. 2 over pi is between 0 and 1, and so I feel pretty confident that the average of this infinity of heights is 2 over pi. And that means that this could fit in here, if drawn to scale. All right, part 3 of station 7. 3 says f of x equals secant x, tangent x, and we're looking on 0 to pi over 4. So 1 over b minus a is the integral from a to b of secant x, tangent x, dx. Well, I know that this is someone's derivative. This is the derivative of secant x from 0 to pi over 4. And don't lose that 4 over pi out in front. Okay, I don't know the secant of pi over 4, but I know the cosine of pi over 4. Cosine of pi over 4 is root 2 over 2. And if I rationalize the numerator, I end up with 1 over root 2. Why did I want to do that? Well, secant is the reciprocal of cosine. So I'm going to have root 2 when I flip that. And if I plug in a 0, secant of 0, well, it's the reciprocal of cosine of 0. Cosine of 0 is 1, so if I flip that, I get 1. And so that times, there's a 4 on top, that's my average value. Okay. Where are we next? 4. 4 says 1 over x on 1 to 4. Okay, 1 over b minus a integral a to b of 1 over x dx. Don't take the derivative here. I get 1/3. Whose derivative is this? It's ln's derivative. We want to evaluate from 1 to 4. So I'm going to have 1/3 ln of 4 minus 1/3 ln of 1. Okay, what's the ln of 1? That's 0. So my answer is going to be 1/3 ln of 4. Now, it's true. I could take this further, algebraically. I could say, hey, this is 2 squared, 2 squared, and I could take this and bring it up as a power. And so now I've got the ln of 2 raised to the 2/3, which I could leave that 2/3 there or bring it down in front. And so we would see 2/3 ln of 2. I think just coming up with 1/3 ln of 4 should be enough, but I can take it a little further. All right, and finally 5. 5 here says this time f of x is a semicircle, 9 minus x squared, and we're looking up at only a quarter of that circle. So I've got this situation here, and I'm not looking for the total of this. I'm looking for the average of this infinite number of heights. I know my value has to be somewhere between 0 and 3. So let's see if we can figure this out. This is going to be 1 over b minus a. 1 over b minus a, 1 b minus a, integral 0 to 3 of square root 9 minus x squared dx. But I don't know how to integrate that. That's right, you don't. But you can appeal to the geometry of the situation and say that this is 1/4 of the area of the circle whose radius is 3. So if I do 1/4 pi r squared, and I plug in 3 there, 3 squared is 9, I get 9 pi over 4 as the value of this integral. Don't forget that times a 1/3. And so 3's will cancel. We have 3 pi over 4 as our answer here. All right, well, I hope those were helpful for you. Here, 3 pi over 4. Let's take a look at station 8. Oh, look, LRAM and RRAM from a table. And what I notice here is that this table, the subinterval width is consistent. But down here with this table, subinterval width is not consistent. So I can use a shortcut here, and I must go the long way here. All right, so given runners information, after so many seconds, how many feet per second are they running? Use LRAM and RRAM with n equals 6. So 1, 2, 3, 5, 6 subintervals, all right. So if I'm doing LRAM, my LRAM is going to be that width times the height plus that width, which is the same, times the left height, not the right one, the left height. It's 1, 2, plus, this is the next subinterval, 1.5 minus 1, I'll do 1/2 again, and I use the height on the left side, 10.8, plus, now we're looking at this subinterval. Subinterval width is 1/2, and my height is the left height, 14.9, plus 1/2, because that's that subinterval width, times the height, 18.1, plus 1/2, and the left height, 19.4. Now, I agree that this would have been a lot less writing if I said, all right, subinterval width is always 1/2, we'll just pull that out as a constant, and add up the first through the second to last to find my LRAM. Okay? Remember, with LRAM, we use that first height, but not the last one, 20.2. But with RRAM, we don't use that first height. We do use the last height with 20.2. So 1/2, 6.2 plus 10.8 plus 14.9 plus 18.1 plus 19.4, and then the last height, 20.2. So this is going to be RRAM. MRAM uses the first and the second to last, and RRAM uses the second to the last. Here, by the way, I ended up with 44.8 for LRAM, and for RRAM, sorry, that one's 44.8. RRAM is 34.7. Okay, so there's our RRAM and our LRAM. If you weren't comfortable taking this from the table and doing it, you may want to take the time to graph those ordered pairs and draw in some rectangles. B says, in station 8, now compute the estimates of the distance traveled using MRAM, but only 3 subintervals. And why are they doing that? Well, so that's one of my intervals. In order to use MRAM, I need to know the value that's halfway from A to B. Well, halfway from 0 to 1 is 1/2. And so I actually know that height. So my subinterval width is going to be 1 minus 8. We are using LRAM. Yeah, my subinterval width is 1 minus 0 times the middle height, 6.3. Plus, now the next one that we're going to go next is this one. It goes from, just like this one, from 0 to 1. The next one goes from 1 to 2. But we're not going to use these y values. I'm going to go halfway across and use this one. So now I've got 2 minus 1 times 14. Plus, and now we come to our last subdivision, n equals 3, 1, 2, and now our third. So here the subinterval width is going to be 3 minus 2 times the middle height, 19.4. Well, you could tidy this up. This is going to be 1, this is going to be 1, this is going to be 1. So I could just get rid of all of this. Oh, can I? No. Yes? Yes. These are all just 1s. And so then really I'm just adding those 3 values. 21.1 plus 19.4 is 40.5. That seemed pretty fast. That seemed pretty reasonable. And since we're given some units here, we know the antiderivative would be feet because velocity is feet per second. Okay, and then problem number 2 says use the trapezoid sum. The subinterval widths are different here, so I'm going to write this one out. 1/2 a base times a height plus 1/2 a base times a height plus a height. So that's 2 plus 1/2 subinterval width 6 minus 4 times 6 plus 7. And now we're going up to 10 minus 6 is 4 times 7 plus 10 plus 1/2 15 minus 10 times, I guess we should call this 10 minus 6 for consistency. Okay, so we've got 15 minus 10, and then 10 plus 11. Next, 10, 15, we've got 1/2, 16 minus 15, times 11 plus 18, and then I think it's finally 1/2 20 minus 16 times 18 plus 30. There we go. That's going to represent the number of barrels of oil spilled. When I do that, I get 218.5 millions of barrels. Well, I wonder if that was the Great Molasses Flood in Boston. No, true event. You should read about it. Great Molasses Flood. Now, station 9. Find the indefinite integral in each case. There are a lot of them. These are really, or supposed to be, pretty comfortable for you. So what's my antiderivative going to be here? It's x to the 3/2, because I added 1 to that. If I take the derivative, this 3/2 comes down. I don't see a 3/2, so there must be something present to undo the 3/2 that comes down. Okay, b is the integral of 1 over x dx, and it would be fabulous, super fabulous, if you said, oh, I know whose derivative you are, you're ln's derivative. But I worry that people, instead of doing the antiderivative here, will do the derivative. And so we have 1 over x squared dx, and it may be helpful to turn that into x to the negative 2. When I go backwards, I'm going to add 1 like that. Add 1 to negative 2, I get minus 1. If I take the derivative of this, that minus 1 comes down. Minus 1 times minus 1 is plus 1. And don't forget, if you subtract 1 here, you get x to the negative 2 times positive. There we go. Same. All right, d. D says the integral of e to the x dx, and we should know that that's e to the x plus c. Oh my goodness, did I leave the c out on the last one? I think I did. So why don't you make sure you have a c there? The integral of cosine x dx, that's just going to be sine x plus c. And how about f? F says the integral of sine x dx, antiderivative of sine, is negative cosine x plus c. That negative, very important. It's very important for this reason. If I take the derivative of this, I have positive cosine x. But I'm doing the antiderivative. Whose derivative is sine? It's negative cosines. Okay. And then, if we did g, integral of 1 over x squared plus 1 dx. And really, if you can't write this one down in seconds, you have got to go back to your integrals and remember that this is the derivative of inverse tangent of x plus c. And no, not finally, there's h. H is the integral 1 over square root of 1 minus x squared. Oh, talk about inverse trig. So the antiderivative of this is going to be sine inverse of x. Now I get to say finally. And we have 5 to the x dx. All right, so how do I do the antiderivative here? It's not a question of adding 1. Oh my god, it's not a question of adding 1. This is not a power function. This is not a polynomial. This is an exponential. And so please, please, please don't turn it into a polynomial where you want to add 1 up here. So I'm going to say 5 to the x. Let's imagine that 5 to the x plus c is my antiderivative. Because you know, if this were e to the x, this would be e to the x. But let's check by taking the derivative here. Derivative of the constant of 0. The derivative of an exponential is that exponential times the element of the base times the derivative of the inside stuff. So I've got that I'm looking for, but I missed that. So when I look at I need something, because I don't see a this here. There must be something on my antiderivative that gets rid of this ln of 5 that will show up when I take the derivative of both sides. And I think that's it. ln of 5. Okay, so let's practice. Take the derivative. 5 to the power of is going to be 5 to the power of times ln of 5 times the derivative of that stuff. And so I get this. Oh, and then there's that ln of 5 on the bottom, and they cancel it, and there's 5 to the x. So don't forget the plus c. No, don't forget the plus c. 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 Station 10. 10 says, given f, find big F prime by taking the derivative. Ah, well, this is a little more FTC part 1 practice. Now we get A, big F equals 0 to x squared, square root 1 minus plus r squared d r. So if I take the derivative to get f prime, oops, I want the derivative with respect to r. Yeah, not. Luckily, derivative times integral does each other in this case in there. And so I have square root of 1 plus x to the 4th. Don't forget to take that derivative, 2x. Done, done, done. Walk away and move on. If I'm looking for part B, my function now says cosine of t over t dt, and this is negative 4, and this is t squared, x t down 4. Okay, derivative on this integral, this pops into both of those places. So we're going to have cosine x to the fourth over x to the fourth. Don't forget the derivative of that is 4x to the fourth. Alright, no, I don't have to use quotient rule here, and I definitely don't have to somehow use quotient rule backwards. But taking the derivative of an integral, hit undo. This comes down into both of those places, and that's the sort of gravy-less Thanksgiving. Don't forget to complete that meal by taking the derivative of that inside function. Okay, we're taking the derivative here, so no plus c. Don't let that enter in as well. Okay, part c says, though, f of x round to x to 0, t squared minus 3t dt, and that's going to be negative 0 e to the x, t squared minus 3t dt. But I'm taking the derivative of both sides, 2 dx. So, the derivative of the integral, they do each other. What moves that negative? This comes in here. So it's going to become e to the x to the second minus 3 times e to the x. And so raise the power to a power and multiply them. 2x minus 3 e to the x. All right, there's big F, big F prime. Took the derivative of an integral. All right, last one on this station, part D, big F of x squared, sine t dt. Now at this point we might have done enough of these that you don't need to split this into two integrals, but I always feel much more confident when I do. Squared. All right, so I'm going to flip these at the bottom lines. Now, I'm not taking the antiderivative here. This is f. I want big F prime. So derivative of the integral goes away. This goes in here. Times the derivative of that inside function. And here, I'm going to flip these. 0 to square. Okay. And subtract. I'll plug a 0 in there. 0, the antiderivative. Oh, there's no antiderivative because I'm taking the derivative of both sides. So it's going to go in there. We're going to have sine x squared times the derivative of that 2x. All right, here's 10d. 11. Let's take a look at 11. 11 says find the average value on the given interval. X equals x minus 3 squared 1, 2, 2. Okay, we want average value. Yeah, so 1 over minus a integral a to b of x minus 3 squared dx. Okay, well that's going to be 1/3. What's my antiderivative here? Yeah, I could FOIL that. X squared minus 6x plus 9 dx. And then figure out the antiderivative of each of these. I feel like I'm missing something. What's exactly that? I know what the average value would be minus a. Okay. And now to build an antiderivative, x to the third over 3 minus 6x squared over 6 minus 9x. So that's going to be that. It's not over 6, it's over 2. And so I'm going to have x to the third over 3 minus 1 half x squared plus 5x. And if we evaluate this antiderivative from 2 to 5, 2 to the third over 3 minus 1 half 2 to the second. And if I plug in my 2's now. 2 to the third minus 3 minus 1 half. Five. All right. I think that's average value. Because we did we do 1 minus 3 here? Integral and plus derivative. 3 minus, sorry, going back, nagging self-doubt. Sometimes it's good to listen. X squared minus 6x plus 9. And we're wanting average values, so we're going to integrate this. X to the third over 3 minus 3x squared plus 9x. And 2. So I need the integral from 2 to 5. X to the third over 3 minus 3x squared plus 9x dx. Antiderivative would be x to the fourth over 12 minus x to the third plus 9x squared over 2. So here's my antiderivative that I want to evaluate from 2 to 5. 2 to the fourth is 16. 16 over 12 is 4 thirds. Minus 2 to the third is 8. Plus 2 squared is 4. 4 divided by 2 is 2. 2 times 9 is 18. So here I'm going to have 10 plus 4 thirds, which is 30 plus 4 thirds. 4, 34 thirds. That's going to be my average value here. That's curious. Last time I did this, I had a value of 1. Take a look at it. Average of all those heights was 1. Oh. Well, let's take a look again. Okay. Average value 1 over b minus a, integral over to b of x squared minus 6x plus 9 dx. Antiderivative x to the third over 3 minus 2 minus 3x squared plus 9x. And don't forget to go from 2 to 5. There's also a 1/3 out in front. So if I plug in 5, I'm going to plug in 5 over 3 minus 3 times 5 squared minus 9 times 5. 75, 45, that's minus 30. And here we have 90. 125 minus 90 over 3. It's 35 over 3 times 3, 49. that is also not 1. Oh, duh. I didn't actually plug in the 2. Let's finish the problem. 2 to the third over 3. 2 times 2 squared plus 9 times 2. Okay, and when I finally do all of this, not forgetting that, that's when I'm supposed to get the number 1. 1 is what you should get if you simplify that. Okay, find x equals c such that the average value of f of x equals 1. What does that mean? Well, if you think about this graph, this x minus 3 squared graph. It's my parabola shifted right 3. And I'm going from 2 to 5. So we're considering this. But now we're talking about this other situation where the function takes on that average value. Where here does the height actually equal 1? The height over here, if I plug a 5 into this function, is going to be 4. And if I plug in this number in here, 4 minus 12 is 9, 4 minus 12 is negative 8 plus 9 is 1. And so if I want to pick up all these heights, I think there are definitely 2 places where the height is equal to 1. So let's consider that. I'm going to take my height function, x minus 3 squared, and I'm going to set that equal to that average value that I want. So I take the square root of both sides. Plus or minus 1 is x minus 3, and add 3 to both sides. Get x equals 1 plus 3, or negative 1 plus 3 is 2. Yeah, and so this function takes on the average value, a value of 1, at 2 different places. One here at 2, one here at 4. There's 4. Says 4. Huh. Oh, why? What is equals 1? Oh, we're going to 5. That's why. So here's 4 here, there's 5. And yes, I did the work correct the first time. Okay, where are we next? Oh my god. Oh, sketch that and same as the, yeah, that's this part that I showed you, where we're looking at this parabola from 2 to 5, and what we're saying is that this shaded area is actually going to be the same as that all of this fills that exactly. And so now we're looking at a big rectangle whose length is 5 minus 2 and whose height is that average value. So 3 times 1 is 3. Okay. What about number 2? F of x is square root of x and 0 to 4. This is 4, 2, because this height is 2. Right over here is 0. We're looking for the average value, 1 over 4 minus 0, integral 0 to 4, x to the 1 half dx. It's going to be 1 over 4, integral 0 to 4 of, what are we supposed to do with that? We are supposed to add 1. But wait, if I take the derivative of this, and then see a 3 halves here, so 2 thirds. This is the antiderivative of that. So I'm looking for this. I could do some canceling. And now I want to know my So this is the square root of that number. Square root of 4 is 2, 2 to the third is 8, 8 times 2 is 16 thirds. Don't forget you've got that 1/4 in front. We still need to consider what happens when we put the 0 in. Well, if I plug a 0 in there, I'm getting 0 times 1/4. So I think 4 thirds is my answer to what's the average value. Yes, we like 4 thirds. And next we're supposed to find when on 0 to 4 does the function have a y value of 4 thirds. So let's take that function and set that function equal to 4 thirds. If I square both sides, I end up with x equals 16 ninths. So that's where this curve takes on the average value. The average value that we had was, what was it? Good question. Our average value was 4 thirds. So when is this y equal to, oh, I see it now. I thought it was a b, 4 over 3. That happens at 16 ninths. When x equals 16 ninths, the y value will be 4 thirds. And doesn't that make sense? Because I'm taking a number and plugging it in there. So if I take the square root of 16, I get 4, and if I take the square root of 9, I get 3. So that feels pretty comfortable. And we were asked to draw that rectangle again. So there's our height of 4 thirds. And what we're saying is this piece will fit nicely in there, and then I'm just finding the area of a rectangle. A rectangle whose length is 4 and whose height is 2. So, yeah, that would be 8. Okay, station 11, station 12. Indefinite integral time. Rule number 1 says the integral of y squared minus 1 over 1 dy. Yeah, no, really, you know so much more algebra. If I split this into these two, it isn't simplified here. Y squared cancels a y. So there's my rewritten indefinite integral. The antiderivative of y is y squared over 2. The antiderivative of 1 over y is 1 of y. And don't forget the plus c because you're going backwards. All right, what's next? 2. The integral of 1 over x plus 1. Well, when I think about finding the value of this indefinite integral, I'm thinking about how come? Well, you know, 1 over u means that f is the element of u. Of course, this would be problematic if there was something in here whose derivative was other than 1. And so when I look here, I think, okay, I'll take the derivative of the outside function. I'll leave the inside alone. And now I come back and take the derivative of the inside. Oh, well, that's great. That's exactly what I have here. And that came from ln of Alexa off, x plus 1, plus c. It's not up time, and it's back. Okay, and then finally, our last problem. Integral -1 n squared x dx. Well, I think that you should recognize that this is -1 times 1 over sine squared. Why? Well, you can pull that negative out. And then what's 1 over sine squared? Ooh, cosecant squared. In fact, I have negative cosecant squared. Whose derivative is negative cosecant squared? Cotangent x. Take the derivative of cotangent, I get negative cosecant squared. So a little manipulation can be good for us. Okay, seem to only be 2 more stations. These are really good stations, though a lot of students get these either partially or completely wrong on the test. Got a little graph here with a straight line and a straight line, and then a concave up and decreasing, and a concave down and decreasing. This is the point 5, 0 here. And this point is 4, 3. And this point is 3, 5. Okay. This is a graph of the velocity of a fish on 0 to 6. So this is V, and this is T. When is this fish swimming to the left? Well, since velocity is positive all this time, that means the fish is swimming to the right on 0 to 5. Once we start swimming past time equal to 5 seconds and start going below that axis, we go left then on 5 to 6. Okay, this fish swimming left. A swims left on 5 to 6 because velocity is less than 0 on 5 to 6. All right, part B, when is the fish stopped? Well, this is a velocity graph. Stopped means V equals 0. And that happens here, T equals 5. C, if x of O, so what does that mean? Well, x of O is the same as S of T evaluated at 0. This is just position. Original position is 4. That's how I understand that statement. And we're asked to find x of 3. So here's my recommendation. That's the antiderivative of that. So if I use my FTC2, I could say x of 3 minus x of 0 is the integral from 0 to 3 of f of x. All right, so the integral from 0 to 3 is that area. Well, we know the height is 5, and we know the length is 3. It's going to be 1/2 5 times 3. Integral from 0 to 3, yeah. And we know that x of 0 is 4, and we're looking for x of 3. Well, if I add 4 to both sides, I'm done. So we have 15 halves plus 8 halves. That is going to be 23 halves. So x of 3 is 23 halves. I believe that's true, but you might want to check that one. When is the fish decelerating? Decelerating. Well, we know acceleration is the slope on velocity. And if we want decelerating, then we want to look at places where there are negative slopes on velocity. Well, velocity, acceleration is less than 0, or v prime is less than 0 on 3, 2, 5, union 5, 2, 6. Why didn't I just do 3 to 6? Because there's a 0 slope at 5. And so then v prime, in fact, will be equal to 0, not less than 0. Yeah, that's it. That's station 13. But no, really, you need to be comfortable with those. I know I'm comfortable with those now, but you need to get comfortable with those. Okay, and our last station, station 14, we've got a graph of x. This point here is called negative 1, 2. This is negative 3, 0. And this is 1, 0. Oh, look, there's this little absolute value thing here. This is 3. This is 4. And that one is at 2. Negative 1. Okay, this is a graph of f. And we're told here if g of x is the integral from 1 to x of f of t dt, then find g of 1, g prime of 1, g double prime of 1. Well, so what am I looking at here? What is the relationship between g and f? Well, if I take the derivative of both sides, I'm going to have dg dx, or g prime, equals derivative undoes integral f of so I understand then that this graph of f is really g prime. So this is g prime that I'm looking at. So if I want to find g prime of 1, no problem. That's just f of 1, which is 0. And if I want to know g double prime of 1, well, that's saying what's the slope on this graph at 1. Yeah, the limit of the slopes from the left side of 1 does not equal the limit of the slopes from the right side of 1. And so I'm going to say that this is undefined. I think undefined is my g double prime. Now, what about g of 1? Well, I know that the integral from 1 to 1 of t dt is 0. And we said that g prime is f. So g is this integral, and g of 1, even though I think it's x here, g of 1 means put a 1 in there. So g is going to be the integral from 1 to 1 of f. And what is that integral? Well, maybe that integral is 0. So g of 1 is 0. Okay, 2 short questions here, and then we're going to be all done with these stations. G is decreasing when g prime is negative. And that, since we know that g prime is our f graph, whenever f is negative, g will be decreasing. So when is that happening? On 1, 2, 3. And when is g concave up? Well, remember, g prime is a graph of f. And so g double prime, where I'd want to check out concavity, is going to be the derivative of f, or the slopes of f. I'm looking for a place where g double prime is greater than 0. I'm looking for the slopes of f being positive slopes. And I have positive slopes on f going from negative 3 to negative 1, union 2 to 4. And that's where g would be concave up. Really, this problem is completely impossible to most students who don't make that connection that when they tell me g of x is really the integral from 1 to x of f of t dt, that when we take the derivative of both sides, g prime is f. I have to come to this understanding probably before I even read any of those parts A, B, and C. All right? Okay, well, there you go. I hope you have great success on this as well as the Chapter 6 test, and let me know if you have more questions. Take care, everyone.